All right, folks, so here is a lesson that combines week 14 Thursday and week 14 Friday on antiderivatives. It should be a pretty short lesson. So basically, if you look over here, what we've been doing is, okay, when you see something like this, okay, when you see something like this, we call it an integral, but what you really think, and what we previously were doing is, like, let's say you have an integral of 1 to 4, and let's say you have 1x, okay, minus 2. So basically, if we were to evaluate this, or conceptualize it, we will conceptualize it as there is a line, in this case a line with a positive slope, and we are looking for, so let's go like this, okay, I said 1x minus 2 here, and I said x equals to 1, x equals to 1, and x equals to 4. So we are looking for the area, okay, the way you conceptualize this orange is we're looking for the area bounded between the graph, okay, let me copy and paste this, okay. We're looking for the area bounded by the graph, the function, and the x-axis, which is here and here, and you add those areas up, and remember, this is a negative area because it's below the x-axis, okay. So the way you read this is that you read it as the definite integral with a lower bound of 1 and an upper bound of 1 of the function 1x minus 2. And again, the way you conceptualize it is that we have this function and we're looking for the total area between this function bounded by this function, the x-axis between the x values of 1 and 4. And 1 and 4 is right here and here, which is the blue and green. Okay? Now, this is called a definite integral because it has bounds 1 and 4, okay? And when you evaluate this definite integral, you basically take the antiderivative, okay? At some point, one of the very first steps is you got to take the antiderivative of this 1x minus 2. Sorry, this thing is kind of in the way right here, this integral piece here, okay? So here we are going, when you see this integral, this one does not have bounds. This is called an indefinite integral, okay, because there is no definite bounds. So it's just basically asking here, what this is basically asking is, what is the antiderivative of 1 over x squared plus 1? And you just say this right here, okay? And we've done that a million times. And here is a list, or over here rather, okay, we have an example where I think I may have went over this in a previous video, but we basically convert this 4x cubed over x. You think about that as 4x squared because 3x is on top, 1x on bottom becomes 4x squared. And then 1 over x, okay, 1 over x, you think about that as x to the power of negative 1, sorry. So at this stage right here, you get x to the power of negative 1, okay? And then you just proceed as usual. Or actually here, you can keep this, okay? You keep this as 1 over x and think about it, and you take the antiderivative, which is ln of x, okay? Ln of absolute value of x, okay? So again, long story short, when you see this symbol here, that's indefinite integral without any bounds, and you just take the antiderivative, okay? That's all it is. Now, what happens, and here's the list of antiderivatives over here, so please keep this in mind. This will be very helpful for you. Okay, now, here, what do you do when you see this integral when it's definite? Okay, so what you do is simply this. Okay, again, this is asking for, if I pop this into Desmos over here and do sine of 2x and then I go 0 and pi over 6, okay? X equals to 0, x equals to pi over 6. It's basically asking for the area bounded by this function and the x-axis right here, okay, by this function and the x-axis. So it's asking for, essentially, right here, boom, boom, it's asking for this orange right here, okay? That's what it's asking for, all right? And this is the 0 is the blue line, the pi over 6 is the green line, okay? So the way we do that is simply, to find that area, what we simply do is take the antiderivative of this, which is that, okay? And then you plug in pi over 6 into x, and you get this. And then you plug in 0 into x, and you get that, and subtract the upper bound, plugging in the upper bound, which is pi over 6, with the plugging in 0 for the lower bound. So you basically subtract the two things that I just said, okay? You plug in pi over 6 into x and you get that, plug in 0, plug in the lower bound into x and you get that, and subtract the plugging in of the upper bound, which is pi over 6, with the plugging of the lower bound. And then you basically get this right here, okay? All right, that's your answer. Okay. Okay. And here at this, you might need to use a unit circle with here and here. Okay. Now, same deal here. Okay. Here you take to get from here to here, you take the antiderivative. Okay, 2 to the power x. The antiderivative is this right here, and you can just use this yellow box right here. Okay. And I think you're going to be using this one right here, okay? Yes, you'll be using that one. Let me just double check. Yeah, you'll be using that one. Anyhow, and then you plug in the upper bound. Whoops. You plug in the upper bound over here. You plug in the upper bound to here, and you get this. You plug in the lower bound into here, all right, and you get this. And then you subtract the two with each other, okay? Yeah, okay? Now, the last part of today's lesson is going to be, oh, and by the way, over here, just as a matter of algebra, they multiply 2 and 2 on top and bottom so that these will match, okay? And you end up getting 32 minus 1, which is 31, all right? And then 61 plus 4 plus 1 is 65, okay? Now here, a ball is thrown vertically upward with a height of 5 feet with initial velocity of 64 feet per second. How long does it take for the ball to reach its maximum height? How high does the ball go? And we got this right here, okay? And instead of per second, we're just going to say second squared. Okay, so here's the deal, folks. Let's just look here, okay, because I don't want to throw too much at you. Let's look at this diagram. I am 5 feet above the ground. I throw the ball, and it makes this parabolic arc, okay? And so we can infer that in regards to position, S of 0 is 5. The position at T of 0 is 5. That's what this is. We can also infer that, or it's just what's given. I shouldn't even say infer. This is just what's given. The initial velocity, V at time 0, is 64 feet per second right here. Okay? So what I was going to say was that the maximum height, okay, how long does it take for the ball to reach its maximum height? We can say that the maximum height at this stage is the maximum height, and that's when velocity is 0. So because the velocity is going, well, let me just say this. The velocity is the velocity at this height right here, this is pretty much right at this moment when the ball stops before it starts descending, so velocity is 0. So we're going to put these 3 items in our back pocket and revisit it very soon, okay? Now, I want you to recall that from October, the derivative of the position function is the velocity function, and the derivative of the velocity function is the acceleration function. And also the double derivative of the second derivative of the position function is the acceleration function. Now, if we just go backwards, we can say that the antiderivative of the velocity function is the position function. All right, so I can literally say like the antiderivative, okay, I'm going to use that integral notation. The antiderivative of the velocity function is equal to the position function, okay, I can say that. And I can also say the antiderivative of the acceleration function is the velocity function, okay? So one of the key things that we're going to be doing here right off the bat, when you see a function like this, okay, we want to go backwards and build the velocity function from this acceleration function and build the position function from the velocity function that we build. Okay, so long story short, we're trying to gain these 2 green highlights here, and once we gain these 2 green highlights, we're ready to rock and roll. Okay, so from here all the way to here is just building the velocity function, building this position function. So here we're going to go again. We're going to take the antiderivative of the acceleration function, which is here, okay. And the antiderivative of this is going to be this plus c, okay. So we're here now, and we're going to plug in 0. See, now we're going to revisit this that we stored in our back pocket over here, and we're going to plug in 0 for t, and we're going to plug in 64 for v of t, okay? And that brings us to here, and we solve backwards, and we get c equals to 64, okay? All right. And so now our velocity function is going to be this gray with a 64 for c. Okay. All right. So this is our velocity function going backwards. Okay. Now we're going to go backwards again to use our velocity function to build our position function. So we're going to take the antiderivative of this right here. So we're going to take the antiderivative of this, which is this right here. Whoops. Which is this right here. And then we're going to take the this becomes that. Okay. All right. And now we're going to plug in, okay, we're going to plug in 0 into the t's right here and here. And we're going to plug in 64 right here, which brings us to this right here. Okay. I don't know why, sorry, I totally messed that one up. I meant plug in the 0 in here from the s of t. Okay, boom, boom, and then plug in the 5 right here, which brings us to here. And then we get c equals to 5. Okay? All right? And that brings us to this function. So as of now, okay, we have the v of t and s of t and a of t. Okay, a, v, and s of t. Now we're ready to rock and roll. Okay? So we know we want the maximum height, and we know that the maximum height v is 0. This is yet another situation where we set velocity equals to 0. It's a very common thing. So we're going to set this right here, the velocity function, equal to 0, which brings us to here. Solve backwards. T is 2 seconds. Okay? Now, what do we do with that t of 2 seconds? It's not asking us for time. It's not asking for when it reaches its maximum height, which is 2. It's asking for it's asking for, oh, sorry, it does right here, okay? But it also asks for how high is it, okay, at t equals, when it reaches its maximum height. So we know it's 2 seconds when it reaches its maximum height. So we just simply plug in 2 seconds now into t right here, into our position function, to find out how high it is at 2 seconds. And that's what happens here. And we get this number 69 here, 69 feet tall, 69 feet high, sorry. Okay, so to zoom out, the big picture is that we're given the A, we jot these down here. We use this information right here and create this, okay? And we store that in our back pocket to use later on, okay? And then we have the acceleration function. We go backwards to build the velocity and position function, okay? That's very standard to do. And then we set velocity function equal to 0, okay? And we get this and solve backwards for t, which is 2 seconds. That at 2 seconds, we get our maximum height. And then we plug in 2 seconds into our position function, and we get 69 feet. Okay, that wraps up today's lesson, folks. Thank you for tuning in.